So today we are going to try to prove that Euclid's proposition 47 is true. And Euclid's proposition 47's enunciation says that in right-angled triangles, the square on the side subtending the right angle is equal to the squares on the sides containing the right angle. And so our given is triangle ABC, and we know that the right angle is at A, so we're trying to prove that the line opposite of the right angle, the square we construct on this will be equal to the square we construct on line BA plus the square constructed on line AC. So for our first statement, we would create those squares. So we would create squares BC, BA, and AC. And a reason for that would be proposition 46, which says that with a given straight line, you can construct a square on that straight line. So we'll construct our squares. And so because of the definition that Euclid gives of a square, which is definition 22, we know that all of the sides of a square are going to be equal to each other. And we also know that all of the angles inside of each square are going to equal one another and also be equal to right angles. So our next step would be to create the line AL. And we're going to create that parallel to line BD and line CE. And we can do that because of Euclid's proposition 31, which says that you can draw a line parallel to a given straight line through a given point. And so our given point would be point A, and our given lines would be BD and CE. And so this would be AL, and we'll mark these parallel to BD and CE. Our next step would be to create the lines AD and FC. And our reason for that is postulate 1, which says that with two given points, you can connect to those points to create a line. After that, we are going to show that this angle right here, which we'll say is angle X, is equal to your right angle. We can prove that through the definition 22 that they are all right angles, just again because it is a square. And we'll also label these H, K, and we'll label this G and then F. Our next step would be to show that the lines CA plus AG is equal to two right angles. And that's just because of proposition 14, which says that if a straight line falls from a given point and those angles add up to two right angles, then it'll be a straight line. And we already know that it has two right angles because that was our given angle. And by constructing a square, you know that all of the angles inside the square are equal to right angles. And so for that same reason, we can show that line BAAH is also equal to two right angles and therefore is a straight line. After that, Euclid goes on to show that the angle at DBC is equal to the angle at FBC. And that's just because of common notion 1. Because the angle at FBA, let me clarify, FBA is what the angle at DBC is equal to. Because we know that those two are both equal to right angles by constructing our squares. And so we would add the angle at ABC to both sides, and therefore we could prove that the whole angle DBA is equal to the whole angle at FBC. And because of common notion 2, which says that if equals are added to equals, the remainder will be equal. So we're going to show that the angle at FBC is equal to the angle at DBA. And so because we have proven that those two angles are equal to each other, we can prove that the triangle at FBC is equal to the triangle at DBA because of proposition 4, which is the proposition that shows if you have two triangles with a side, another side, and an angle equal to each other, then those entire triangles will be equal to each other. Our next step would be to show that the parallelogram at BL is going to be equal to 2 of the triangle at DBA. And that is just because of proposition 41. And what proposition 41 says that if a parallelogram shares a base with a triangle and falls in between the same parallel lines, that the triangle would be double that of the parallelogram. And so our parallelogram is BL and our triangle is DBA, and they share the common base DB, and they fall in between the same parallels that are AL and BD. And so for that same reason, you can show that the square of AB, the square on AB, is equal to the triangle FBC. Which again is just showing that they fall in between the same parallel lines and they share a common base. So by showing that, you can similarly show that the parallelogram of BL is equal to the square of AB. And that is just because of common notion 1, because those equals are equal to the same thing. So then you show that this square is going to be equal to this parallelogram. And so similarly, you would show that this entire square is equal to this parallelogram by constructing the lines of BK and AE. Again, using postulate 1, just connecting 2 points to create a straight line. And so by going through those same steps, you would be able to prove that the square on AC is equal to the parallelogram of CL. And so by doing that, by adding the square on AC plus the square on BA, it would come to equal this whole square on BC. And that is how Euclid solves the Pythagorean theorem.